Hey there, Unit 5, Lesson 4, our warm-up. What number times itself equals 25? So I always do a what number times what number equals 25. Five times 5 equals 25. And I mean, when I was first learning squares, I'd make a list on the side of my paper. 1 squared equals 1, 2 squared equals 4, 3 squared equals, just kidding, 9, 4 squared equals 16, etc. Okay, it's something that is really nice to have memorized, but if you don't, you can just make a list or use your calculator. What number times itself equals 81? It's like x times x equals 81. X squared equals 81. If I take the square root of both sides, x equals 9. What number times itself equals 10? I don't have a perfect square for 10. Okay, there's nothing that I could actually do. If I take my calculator and do square root of 10, oops, I get 3.16227766. I think it goes on forever. Because if I actually typed in 3.16227766 times 3.16227 whatever, I get 9.999999. I don't get 10. So what number times itself is equal to 10? Square root of 10. I can say that the square root of 10 times the square root of 10 equals 10. Okay, I can show you here. Square root of 10 times square root of 10. Square root of 10 times the square root of 10. 10. It's not magic, it's math. Moving on. All right, scaling up a rectangle. Here's a rectangle with length 5 units and width 2 units. What is the area of this rectangle? I have 1, 2, 3, 4, 5 times 2. The area of this rectangle is 10 units squared. All right, if we dilate this rectangle from point A by a scale factor of 2, so that's my center of dilation. If I'm going by a factor of 2, that means I'm going up to here, D prime. This is 5, so 1, 2, 3, 4, 5. B prime, and C is going to, if I had a straight edge, I would go from there. That means I can go straight out, and I would end up, there's my dilation. Calculate the area of the image. So this side is now 10, and this side is 4. So I'm at, 40 units squared. Okay, now dilate the original rectangle from point A by a scale factor of 3. So 1, 2, 3, 4, 5. So we went from the original one. So D double prime, C double prime, B double prime. And the area of this, so I should, this would be length times width, right? And this one's going to be length times width. And then we did green. I've got length, 2, 4, 6, times width, 5, 10, 15. And that's going to give us 30, 90. Right? 6 times 15, yep. Okay, then complete the table. All right, so the area of the image, scale factor of 1, our area was 10. A scale factor of 2, our area was 40. Scale factor of 3, our area was 90. These are all units squared. Factor by which the area changed. So from a scale factor of, so we went from 10 to 40, my factor is 4. I did it times 4, right? When I went from 4 to 90, 40 to 90, when I have a scale factor of 3, I'm doing it times 9. So let's just do it here. Times 4 times 9 from the original, which is a scale factor of 1. Okay, we didn't do any of these other calculations, so let's hold off on them for a second. All right. All right, if we did a scale factor of 4, that would mean my length would change by 2, 4, 6, 8, and my width would change by 5, 10, 15, 20. And my area would be 160 units squared. And from my original, that would be a times 16. That times looks a little wonky. We're going to get rid of that. Okay, if we went by a scale factor of a half, we didn't do that one. That means I would be here to there. And that would be a 1 times 2.5, so our area would be 2.5. So to get from original down to there, I'd have to multiply it by I'd have to multiply it by 0.25. I made a mistake. Did you catch that? Oh. If I had a scale factor of 2.5, okay, what do you think we're going to have? Our length is going to, original length was 2 times 2.5. And then our original width was 5 times 2.5. So 2 times 2.5 is 5. 5 times 2.5 is 12.5. So that area is going to be and to get from here to here, be a scale factor of 6.25, okay? So write an expression for the area of a rectangle with length and width. Length times width equals area. All right? Imagine dilating the rectangle with length L and width W by a factor of K. That means we have length times K times width, Okay, you see where we're going yet? It's pretty cool. Now write an expression for the area of the dilated rectangle. I'm actually going to take this one a bit further. I have like terms. I can actually factor out a K. Well, no, we're not going to do that. I'm going to go ahead and multiply everything. We've got LK times WK. That gives me L times W times K squared. Because I have two K's, I make it K squared. So I'd actually write that out front. K squared times length times width equals area. Use your work to draw a conclusion about what happens to the area of the rectangle when it's dilated by a scale factor of K. The area changes by K squared. right? If we take this original area with our scale factor of 1 and we multiply it, 2 squared equals 4. Okay, 2.5 squared equals 6.25. 3 squared equals 9. 4 squared equals 16. And 0.5 squared equals 0.25. And we could say 1 squared equals 1. All right, so that just shows us that when we dilate something, the area changes by a scale factor of k squared. Okay? That's a big deal, all right? All right, what about other shapes? Andre says we know that if a rectangle is scaled by a factor of k, the area scales by a factor of k squared. Does this apply to other shapes? It does. Jada says, here's a shape that's not a rectangle. Say its area is a square units. Let's draw some rectangles on so it gets smaller and smaller to fit the remaining empty space. We could draw an infinite number of rectangles to fill this empty space. Okay? What I've told students in the past is this is very similar to what we do in calculus, right? This is how we find the area of strange shapes, is we fill it with shapes we know how to calculate, like rectangles and trapezoids, and calculate the area of those so we can approximate the area of strange shapes. So we just filled it with lots of rectangles, and we can always find the area of rectangles. I don't know why that E is not writing. By finding the length and the width of each one. These rectangles start to make a nice approximation of the blob. If we wanted to get closer, we could add even more rectangles. And the sum, which is the addition, the sum of the areas of all the rectangles would add up to the area of the blob. I think we're almost there. It's very true. Suppose the blob is dilated by a factor of k. In doing this, the rectangles covering the blob also get dilated by a factor of k. And when we say that, we mean the length gets dilated by k and the width gets dilated by k. How does the area of each dilated rectangle compare to the area of its original rectangle? We dilated the area by k squared. What does this tell you about the area of the dilated image? Please explain your reasoning. The area of the dilated image would be the original area times k squared would be our new area. Suppose a circle has 20 square inches, has an area of 20 square inches, and it's dilated using a scale factor of 6. The area of the image is 20 times our scale factor squared, which is 20 times 36, which is 720 units squared. This cool down, nope, we're not going to do that because I use those cool downs for other things, so we're not going to do that right now. All right, good job.